Water.
Hello, sir. Hello, sir. Hello, sir.
Yes. Derek, I see your screen. Yeah.
So I actually focused on the first lab exercise to get the whole concept very, very well.
Okay.
I did some of the second two lab tests, but the focus, because the first one is really few, so that I'll try to wrap my head and understand it very well. So the focus was on that, the first lab test.
Okay. And the first lab was mainly on what?
Hello, sir.
Yeah, go ahead. I'm asking, the first lab was on what?
On the LMC,
Okay.
just store a digit and load it
Okay.
out.
That's fine. So let's go ahead. Walk us through.
Yes. Okay, so here are the codes with five lines, or I say 5 instructions. So I ran it, and what I realized was, immediately I ran it, some numbers are stored in the first 4 or 5 mailboxes at the top here. So these numbers are showing the opcode. So when it asks you to input a digit, I input 11 and hit enter. So let me pause it. One thing I noticed was, when you hit enter and the machine starts running, the little computer starts running, you realize the program counter digits changes as it goes on, or as the instructions are being executed. The program counter changes until it gets to 5. So I realized that means it is counting the number of lines, or the number of codes we have, or we wrote for the LMC, right? And at each line, it goes to fetch the instruction register, goes to fetch what it's in the mailbox. So for the first one, for the input, it fetches the 901 and brings it back, and it leaves the 01, the last 2 digits in the address register, and the first 9, the first number in the instruction register.
Derek.
Right then, sir.
Derek.
Hello, sir.
What did you say the program counter is doing?
Hello, sir. It is checking the number of programs, or the number of lines we have in this area, the assembly language code.
So you need to, you see, when you are learning and you're not too sure about something, that is why there is research. So you need to quickly research and say, okay, program counter, what is it doing? More so, aside the materials I've shared on on Sakai, you will do yourself very good. And because right now, I want you have to speak the language of computer. And then this is like the jargons within the field, and it starts from here. The jargons, everything. But once you are done with this course, all the jargons in computing will be, you see, they are all here. So when you talk about program counter within the CPU, it's very, very important. So when you simply say it is counting the lines of code, you are not right per se. Okay. So I want you to come back again and tell me, what do you think the program counter is doing? Because you have experimented, you have observed, and you have seen how it is counting whatever is coming in. So tell us again, what is the program counter doing?
It is reading the lines of codes we have in there.
No, but so right now you have, let's say 2. Yeah, it has 2 in there. Is the lines of code 2? The lines of code you have is not 2, it's more than 2. So I think the program counter is not counting well. Who can tell us what the program counter is doing? I mentioned the last time, but yeah, Emmanuel.
So please, it holds the address of the next instruction to be executed.
It is not holding address per se, but the next instruction to be counted is very important. Okay, so it's holding which kind of address? I want you to be very specific. Which address is it holding? But there are several addresses in the system. You know, because we have several addresses, we should know which of the addresses is holding. Which address? Yes, Emmanuel, come again. You should know, not that you don't know. Emmanuel. Okay, Enoch. Help Emmanuel, clarify it for Emmanuel. So it's holding.
It's the memory address.
The memory address. So Emmanuel, it is not just holding an address, okay? Because there are several addresses in the system. It's not only memory that has an address. There are several addresses in the system. So then, which of the addresses is it holding? The memory address, which is very important. So it's holding the memory address of the next instruction to be executed. Do you understand? That is what the program counter is doing.
Okay.
And it's very, very important in this manner to be able to think about it from that way. And that, so you see, with the program counter, it's sitting right in the CPU. So then, if the CPU needs to track the sequence of instructions that is executing, it's the program counter it goes to check to know. So I will really appreciate that all of you, from this day onwards, you should make yourself ready. And then when you are reading, when you are playing one, when you are doing anything that you think that, oh no, this one, what is it? Quickly check it and fill your brains with it, because the jargons in the field are from here, the jargons. And you must get it right.
Yes,
are we
sir.
together?
Yes, sir.
Good. So thank you, Emmanuel. Thank you, Enoch, and Derek, let's go ahead. So continue. So be very technical, Derek. Don't be speaking too much loose. How do you call it? Like those who are not who have not done architecture. Okay. So you must be very technical as you talk about these things, especially explaining what you are talking. Be very technical.
Okay, sir.
So go on.
Okay, so as my colleague says, you can see so as my colleague said, you can see the program counter holds the memory address for the next instruction to be executed. These people. Right, so when we get to the line 2, that's to load what's in the mailbox here. The address register does its job. It comes to this memory address and pastes it into the accumulator. Then when we get to the this instruction that is out, the accumulator sends what we
which
imputed.
Instruction that is out? Which one?
The fourth instruction, sir.
Okay, go ahead.
So after the address register has picked what we stored at in this memory at mailbox 90 into the accumulator, it sends it through on the buses into the output. Then the program halts for the last instruction. So that is basically some of the things that I observed.
But the activity expected to me left and right. The one who is muting me, stop, okay? The program, that lab activity expected to have a table of every run and what you see at the program counter, the instruction register, and then the accumulator. Did you do that? Did you know what the instruction register is doing? Did you notice what the accumulator was doing? Okay, so we'll come back to you, Derek. Let's take another person who also attempted to go through this. So on share your screen, who else was able to go through the lab activities to tell us what you have been able to achieve?
So please, I have a short note, but then I haven't, like, I've closed the application already. So unless, if I could share the note I have.
Okay. Prince, you can go ahead and share. Let's see what you have. And then after Prince, who else wants to demonstrate? Because you should be able to complete these activities as you move along. So I know you are working. That's the only way I can be sure you are working. All right. Sure. Prince, if you are speaking, we are not hearing you because you are muted. So unmute yourself so we can hear you.
Okay, please, can I be heard?
Prince.
Yes, hello, sir.
Okay, so maybe if you want to set your microphones, do so whilst we take another person and then we can come back to you if you are only hearing me.
Is this the little note I had? So the instruction asked that at the lab manual, we were to enter these codes and then run it step by step and observe the program counter, the instruction register, the accumulator. We should observe them at each step. So I entered the code, and this is the result I had. At step 1, the program counter was showing 1, as we have it here. The address register 9, the accumulator 9. Sorry, the instruction register 9, accumulator 9, and then the
accumulator. I'm seeing 00, but I say 9.
Sorry, sir. Accumulator is 00. Sorry. And then step 2. Now the program counter moves to 2, and then the address register goes to 3.
So before you go to step 2, what does it mean in step 1? All these numbers. What does it, or how did you understand them?
Okay, so in step 1, program counter is showing that it is just we are moving to, or we are running the line 1 of the codes. So we are running the line 1 of the code, which says input here, and then the address instruction register showing 9. I think I would have to run the codes on the app itself so we can follow proper. So please let me quickly run. Oh, shit. Sorry, it's not this one.
It's not this one. Okay.
Yes. So please, could you remind me with the Up again. Harrison something. What is it?
Little man computer.
Computer.
Little man computer. Okay. No, not the 101. We have the other one.
Yes.
CPU, yes, CPU. OS oscillator, yes. Let's use the little man computer. Yes, like that.
No, the CPU simulator cannot run the program you're talking about.
Yes. So I'm using the little man. But even with this one, we can't run it step by step. All right, so this is the one I used. To have the code here. Then I go step.
It seems like you are still searching for something. It's not showing.
Can you hear you? Say something. What's happening?
I mean, your search bar is showing, not the yeah.
We
So
can
now
see it
it's
now.
okay.
We can see it now.
You can see it.
Yes. Yes.
All right.
Yeah.
So now I go step one. I click on the step to get a step one, and we can see it running. So step one, program counter shows us one, meaning it has started to run the first line of the code, and then the instruction register showing 9, and our address register is also showing 1. So please, are you there?
Yeah, we
Yeah,
are
I'm
there.
here.
Okay. So that's it, and then it asks you to input your figure. As the line 1 says, input the figure. So if I go, sorry, so I'm having a bit of a difficulty here. This should be step here, so I can go to the next step. But then that's the process I followed. If I go to the next step, to ask me to input the figure, which here I input.
I understand. I understand, but the question is that when you are getting these numbers, the activity wants to let you understand the essence of program counter, the essence of instruction register, what the accumulator is doing, and what the address register is doing. Okay, so once you are observing them, that's one. Okay, so I click on this. I see from input, it's moving into memory. Something is changing a PC program counter. What number is that? What kind of address is that? Why is it so? Okay, then you are trying to understand the whole phenomenon, because it's like the liver, the lungs, the heart, the small intestines. When food goes into the mouth, okay, so when you use the mouth, as you know, the mouth is like the entry point of anything to the stomach, and then whatever it comes out through your the large intestines, anus. So then when something go in there, where does it get into first? How does the processes go on? who picks what, who picks that before you get it out. So now see your input as your mouth, see your output as in the human body, those who do biology. So now those of us who are doing computer science, it's the same thing we are doing now. Our input, so we have our instruction, which the food is coming in. As they come in, things are moving through to a place. Then we are checking the heart. Is the heart beating? Is the lungs working well? Is this one doing that? And we are checking. That is the kind of mental thing you have to understand with this computer architecture thing we are doing. And I want to say this in this class. Brethren, here, you will have to take this thing seriously. And you will have to do a lot of work on this thing that we are doing. Okay? If I give you activities like this and you don't pay much attention to it, to try to understand why things are happening that way, we'll lose sight of many things. So, Prince, you have done the work. Like I was asking this guy earlier on, you have done it. This one is good. You have your table or you have your steps. At every run, we see 1 in program counter. 9 is in the instruction register. What is this 9, which is in instruction register? What is this 1, which is in program counter? What is this 1 in address register? And why is accumulator 000, like you have indicated? That is what you must understand that. Once you know that and you are moving to a next step and everything is changing, you know why it is changing. Because you know what is in there. Yes, Prince Wilson, you want to add something to it? Abaji, stay on. Don't close. Yes, Wilson. Let's hear from you.
Yes, sir. Hello, sir. Please, can you hear me? Can you hear me clearly?
Yeah, we hear you.
Okay. So initially, I was trying to share what I had done. However, my sound was bad. So let me just use what he is sharing. So the first one, the program counter is at 01, implying that the instruction to be executed next is on line 1.
On
The
line 1.
instruction yes, please.
Good.
The instruction,
Because we have said that at all times, program counter is holding what? The next instruction to be what? Executed. So this
yes,
is
sir.
some of the things you must understand. So in fact, when you understand it this way, you don't need to memorize it all.
Yeah.
Are we all together, class? No,
Yes,
stay
sir. Yes,
on.
sir.
Abaji, stay on, don't close. Stay
Yes,
on.
sir.
Abaji, come back. Abaji,
Yes,
come
sir.
back.
Okay, sir.
Okay, Rosen, go ahead.
All right. And then the instruction register is holding 9. So I did a little research into what the 9 was about, and I realized it doesn't really correspond with any of the values here. However, it is the opcode for the particular instruction you are using, if I get it right. That's what my little background research told me. So for example, each single instruction we input here has a particular opcode it is tied to. And then this 9 here being tied to the
And what
STA.
is opcode? You should know, all of you should know. Don't tell me, but I mean all of you know, because you have done intro to computer science where opcode was discussed there, right? Because if you do not know what opcode is, we are in trouble. And then what operand is, we are in trouble. Do you know what operand is? Do you know what opcode is? You've done intro to computer science where you might have done number systems. Okay, I see more hands say they know. So go ahead, Wilson.
Yes, sir. So the opcode, it's just the value, a number value that specifies like a particular operation being performed. In this case, the STA function, the instruction STA. So the 9 is holding the opcode of the instruction to be executed. The address register is now standing on 01. It is telling us which exactly points in the memory that, which exact points in the memory that we are going to be fetching data from. Every single line of instruction here has been tailored to a corresponding memory location. So currently 00 will be held in position 01. According to this very little man computer structure, 00 is being held in, the input is being held in 00, and then 01 is being held, has the storage over there. So the address register is currently pointing to 01 to imply that currently we are standing on line 1, and then line 1 is being held inside storage space 1. That's the address register. And the reason why the accumulator is at 0 is we have not yet done a mathematical operation yet. Therefore, there has not been any mathematical process. I believe if we run the code further, the accumulator is going to update so that it reflects the operations that are being processed as we move. Sir, please, have I covered it right?
Yes, you have. You have. You have. And all your friends are giving you stars, whether they understand or they don't. They are showing you love and showing you. Some people also show amazing maths, so it's good for you and them as well. Good. Any other person who tried something else to share for us to see? But I think that we are making progress, but it is very slow to me. The reason is that we are 120 now on the call. So when I said who wants to, I should have seen 100 people showing hands. Then I know that 100 people have attempted to work. But when everybody is down, it's a cause to worry. Everybody is down. We have to talk before 2-3 people will come and show up that they want to. You laugh at me, eh? Laugh at me. Another time I'll be laughing at you. Today it's your turn to laugh at me, so you laugh. Sometimes you can all be laughing at you. So
please stop laughing.
Oh, let them laugh. So you see, it is worrying when a class of this number, an activity lab is given, and only 2 people or 3 people are showing you that they have done it, and the rest, no evidence. So let's see if other persons did something. Any lady in the class who also attempted to do the labs, and you see the activities are there, the labs are there. I expect that you would vigorously do, and the reports. I've told you to write the reports. So the report must be written. Any instruction is telling you augment everything as it is. Yes, one of the ladies. Where is Hazel?
Yes, Prof. Please, I'm here.
Yes, share your screen. Let me see what you've done.
Well, I'm finding it difficult to join with my PC. That's why. So at the moment, I'm joining with my phone.
Okay.
Abena Mami.
Where is Abena Mami? Vida, Abena Mami, where are you?
Sir, please, I'm here. The Vida is here.
Yes, Abena Mami and Vida. Share your screen in tens and let's see what you also did.
Okay, I don't really understand the code, but I can share my screen.
No, why don't you understand the code? Now share your screen anyway. Wilson has just explained. So based on the explanation of Wilson, attempt to also explain what you've done. So share your screen.
Oh God. So I can't share my screen. No. I'm not allowed to share the screen.
Everybody has the power to share screen.
Okay. So no, like I can't share.
But which screen is showing?
We can see.
Someone is sharing. Is it my screen?
That's Vida.
It's your
Or that's not
screen.
Vida.
It's your screen.
All right. So please, can you see the screen now?
Yes, we see.
Yes.
Okay. So me, it was today that I'm learning this one, but for this,
I gave the things you 1 week ago. I saying today that you are learning this one. Oh, Vida. Eh?
I've even watched YouTube channel. Like I'm not understanding it. I'm confused.
Vida.
Say,
you are confused. You were trying to watch YouTube
yes.
videos.
Abena Mami can do it.
And what else?
So do you know? Oh.
Tell me, I'm listening. I'm here. I'm listening. Forget about all those who are laughing. Just talk to me.
So for me, I was concentrating on the CPU simulator. You see? So please, can you see it?
Yeah, I can see.
Okay. So what I can recollect right now is this one. You come to the select register set size. which like I can do that one if they said I should do it. I can change the general purpose CPU register. Right?
No,
maybe to
so you do it. Let's see. Just do what you can do. Let's see. You have the thing before you. So let's see.
Yeah, so I can change this one to 8. And I can come to this side. And maybe I want to enter a program name. So I did that. Yeah, hello. Please, you said?
I can't see your screen right now. I can't see you.
Yeah, but we can see. So go ahead. Refresh your page if you cannot see. We can see. So.
Okay, so this one will come here. You enter any the program name, maybe your own program name, and I did that, and maybe the base address, and I said the base address should be 4. Or okay, so let me change it to let me change it to 8. Okay, it should be 4. Then I'll add it, and it will appear in my program list. Please, can you see that one?
Yeah, we are checking.
So it's appear in my program list. So so far, and from the program list, I think you go somewhere too. So far, this is what's and you can come to the instruction. And you can come to the instruction here, and you can add maybe you can add this
So all the instructions, you should know them. I hope you know all of them. At least you have shown effort that you are working. So we have to appreciate that. No two ways about that. And I appreciate it a lot. That at least you have shown evidence that you are doing something. Far better for me at this stage. So keep pushing harder on it, Vida. You will get it. You surely get it.
Sure, sir. Thank you so much.
Good. Abena, let's go. You have done well.
Sir, please, can you hear me?
Your voice is 100 yards away, very far.
I think it's from my laptop. Hello.
So try and speak louder.
I'm having a chest pain, so I don't think I'll be able to speak louder.
Okay. I'm not sure whether the others are hearing you clearly, but whatever the case,
yes, sir, we can hear her. We like it like that.
Let's go. Who like it like that? Head like bomb. If you like it like that. Abna, go ahead.
Yes, sir. I'm trying to share my screen. I don't know if it's working. Please, can you see my screen?
Yes.
Yes.
But not the activity. So you may want to switch to the activity screen.
Please, can you see?
Yes.
Yes.
Okay, so I started working on it today.
Because you're coming to class today.
I really have a lot on my plate, so I haven't really had time for anything this week.
What are on your plate? Eggs, bananas, okras.
No, I'm a nurse. I'm a nursing mother. My mom had an accident some days ago. My grandma died some days ago. So there's a lot, and then plus work too. So juggling everything is a lot for me.
I hear you.
Yes.
It shall be well, okay?
Amen.
We'll take them off one by one.
Yes, sir.
All right. So then let us not trouble. I don't want to add anything to your plate anymore. Brony, Sewa, Sandra, come and relieve Abna so she will not have me also on her plate. I'm not sure she has to space. Yeah, Sandra, let's go. Maybe after Sandra, then I'll move on because the people have not repented yet.
No.
Sandra. Hey, or you came to say no, and left. Okay, so if Sandra is not ready.
Hello, sir.
Yes.
Sir, please, this Vida. Sir, please, I would like you to take us through the little man computers more and the CPU OS simulator more. Sir, please.
What do you want me to take you through? Tell me exactly what you want to know.
So like maybe you will share your screen and you teach us maybe one or.
I don't share my screen. No. Don't tell me share my screen. I'm teaching you. All activities and labs are the students who share their screen.
Okay, so maybe I'll share my screen and you demonstrate. Yeah, and you demonstrate some of you taking the lab, like you demonstrate it to us first. Then we'll pick it from there.
So, Vida.
Okay.
Share your screen. Pause the medical school, where the medical students are expected to know everything about the human body. Because it doesn't matter the kind of medicine you do, you are going to work with the human body. So whether you're a pharmacist or whatever, you must understand the human body so that you appreciate whatever instruction you're going to give tomorrow, whether in the form of medications or in the labs or anything, you know what is happening in the human body. So the human body has different components. Do you agree with me on that, Vida?
Yes, please.
And all these components work together to ensure that things are effectively, discharged within the human body. So now, when we come to computer science or the computing science domain, one of the things that every computer scientist needs to know is how this computer system that we are holding in our hands, whether mobile phones or just the computer system, how does it work? So critically, we must know how it works. You know, when you were in the primary schools or wherever, we have been taught there are 4 components of the computer system: the mouse, the monitor, the system unit, the keyboard and mouse, right? And then as you move along, they now tell, okay, let's open the system unit. And they open the system unit and tell you that in the system unit, we have the motherboard. Then now the motherboard, they start telling you we have the memory, we have this. And now you understand this. How is that? Am I correct?
Yes, please, you are.
Good. But at that level, it is not enough to just know that this is memory, this is motherboard, this is a hard disk. this is IO ports or whatever it is. It's not just enough. The knowledge at this level is that I am going to write a number of instructions for the computer to work with it. It's just like a doctor prescribing medicine for somebody to train. Okay, you are going to write a lot of programs. I'm going to write a number of instructions. I'm going to tell the system on how to work on many things, either designing, whether databases, anything I'm going to give to the system must work on it. But you, the developer, or you, the computer scientist, must appreciate what is getting into the system, which is the inputs, how the processes are going to be done, and how to get out of it. Okay, so now the computer, the heart of it is the central processing unit and then the main memories, okay, or the main memory itself. So then the interaction between the main memory and then the CPU is what we are trying to let you understand using the little man computer and then the CPU simulator, okay? That's what we are trying to let you understand. But at the end of the day, the little man computer and the CPU simulator, all what they are telling us is that, you see, I told you in a very friendly manner that everybody must have your screwdrivers, open your laptops, okay? You are going to unscrew your laptops and then bring out the CPU in there, okay? When we even bring the CPU out of your system, we still cannot see the internal workings of the CPU. If I bring so okay, this is program counter, you don't even see how do you see program counter? But the only way we can appreciate how the internal workings of the computer system is working is to be able to see it through a simulation point of view, or to simulate it to see how it works. So these simulators are showing you directly what happens in your CPU and its connection or communication with your memory. Do you understand? But yes, like you know, when you put food in your mouth, it just doesn't get to your stomach and then it starts giving you blood, isn't it? Yeah. So then when I put data into the computer system, it just doesn't give me the outcome information. No, many things do happen, like food in your mouth. We know that they say digestion takes place where? In the mouth. In the mouth. Good. And therefore, yeah, so when you have anything, you put it in there, you expect that there are a number of things that come to play, digestion is taking place, then the food is now moving through the esophagus, right? Down, many things are happening in the stomach, things are passing through here, a lot of things. So then in the CPU, it is not only the instruction that you have written that is going to do, what do you call it? That is just going to get you the output. The CPU has several components. The three broad components that we have been taught many years ago was the CU, which is the control unit, then the ALU, the arithmetic and logic unit, and then the registers. So usually these are the three main components we'll draw. Anytime we draw a block diagram for you to see the CPU and how it works, we always say it contains the ALU, the CU, and then the registers. Okay, but within this are many other things, and this is what we are showing you, that in the CPU many things are happening in there. There are different components who are in charge of whatever is happening, and then they make sure that things are coordinated to get us the output we are looking for. Does that make sense? Yes, please. Good. So we come to this environment. So this environment is showing you all those. You see, we say CPU has registers. What are the registers? There are a lot of them. We have the program counter, the memory address register, the instruction register, the memory, what do you call it? The memory buffer register. There are a lot of them. All of them are to store. So when you say that the registers are storing data that are being fetched from CPU, it's not just a block called memory, a register, but in that register block, there are different other special registers that are doing the work for CPU. When you go to the execution point, we know that the execution point, surely you need to know what is happening with the cache. So that's I mentioned the level 1 cache, level 2 cache, and those cache systems. And of course, CPU will always work on data and instructions, or is doing both data and instruction. That's how we have the data address, and we have the control address bus and the rest. So as you see within the cache pipeline execution unit, all the things you see there are exactly what CPU needs within to work with. I mean, whenever we need to select the kind of instruction set or the kind of data that we are passing through it. So if you look down there, we see the program control itself, where CPU, when you want to run a program, how do you run it? How do you step back through them? When you have your compilation, how things go on, your input, output, the interpreters, and the interrupts that goes on, because you have been taught already in maybe into the computer science or other courses that anytime program is running, there are interrupts. For example, you're on the highway driving, sometimes there are interrupts, which comes in the form of police, ambulance, fire service, or whatever. All these are components that are in here. Okay, so it's not about coming to walk you through that. Okay, go and click on this this one and do ABC. That makes anything. What you need to do is you have to explore. You are computer scientists. I need to teach the concept. You have to go and explore by doing the labs. And why should you be there and want me to come and write one line here and show, okay, the thing is going through this? I even thought I did those things already. I asked you to explore further. So, Vida.
Yes, sir.
I think by this explanation, you should be fine, right?
Yes, please.
Or you are, until the teacher do one, you have not, you can't see that you have not done anything. Eh?
No.
You want the teacher to do it. You want me to do it before you say I've done something. But
Yeah,
I won't do it.
yes, sir.
Yes, sir.
I won't do it.
Yes, sir. We want you to do it today.
You will learn by demonstration. You will learn by doing.
We
You will learn by doing.
Sir, at least one.
What is one?
We want you to do it so that we can learn from you.
Enoch just did one. Wilson just did one. So what is 111 from?
We beg.
Wilson just did one. Enoch just did one. So what is the fuss about?
No, yours will be different from
you use the
and say mine will do something. Did they?
Okay, sir. Thank you so much.
Yeah, welcome,
Thank you.
Vida. People are in trouble. You don't want to work. It's not that you can't do this. You look at.
It's not like we don't want to work.
But it is like what? It is like Abraham place. Eh? It is like that one.
Sir, it is like you open the thing, you don't understand, you don't know where to start.
Your plates are full. That's all. It is like Abraham plate this week. So it's not about
Intiasia no.
Ben. Then I mean something you. I'm not Intiasia Ben. Oh, there you see.
Yeah,
take a book, read, open up your mind, and don't tell me that. No, this is a simple English you can read. Can't you see special CPU registers? Can't you see general purpose CPU registers? And I've told you already that the CPU already contains all these things. I've already walked you through to see how it works. And what again? Baby, you are not a person. Baby, you are not. Oh.
Okay, sir. So please, can I stop sharing the screen?
No, don't stop sharing. Your friends want to see the other side. So go to the other side. Let them see that one too.
Sir,
why
please,
they would not want to explore? Okay, why they don't want to explore this? I don't understand.
Please,
tell me why they don't want to explore this. I'm giving you laughs. So all you do is the laughs. I'm going to add more laughs to you. So you better brace yourself and start working.
All right, sir.
Yes, Abna.
Please, with Vida's CPU simulator, I'm trying to search for the particular output, but I don't know where it's from. What I'm getting is different.
I don't get it. No, there are two simulators you are working with now. You are working with two simulators now.
The little man.
Yeah, we are working with little man computer.
And then you're also working with a CPU, OS simulator. So there are two. This one and what Vida is showing. You're working with both.
So, like, I want to know where that particular simulator, because when I search for it, it's only giving me pictures, but not where you can work on.
So, share it. I think you have the link the last time I gave you, right? So share it your group page for him.
Thank you.
All right, sir.
Yeah. Share it your group page for him. So for these ones, there are things that you should be able to explore. and explore them. I've given you instructions in the lab manual. Explore them. Otherwise, why are you here? If I have to come and teach you everything.
That we will explore them.
Excellent.
Excellent.
You need to explore. You can't let me teach you everything. I say, hey, explore the little one computer. These are basic simulators. At least your friends have shown that they have control over them. So just get your friends who understand the thing to walk you through, and you should be fine. What else? No big deal. And I've also indicated to you that the outline I gave you, okay, the course outline I gave you, there are specific activities listed in there. I hope some of you have all seen it.
Yes, please.
There are activities there, and then there's a quiz and other things stated in there. Please don't take any of them for granted. I'm going to create the links on Sakai for you to upload, and then the quizzes will be running as such. Don't take them for granted. If I say go and read this book, this chapter, that read it. It will help you. You know, if you fail to do that, that one, don't come to me. So you need to read. You need to read. We shall see. We shall see. Yes, now, any question, any comments?
So please, I have a question.
Please go ahead.
Please, when does IT get easy? Or it gets worse?
IT is easy from day one. Abna, IT is very easy.
Okay.
That's why you are here. IT is very, very easy, especially if you are able to appreciate the workings of IT, whatever you are seeing on the screen. If you understand it, that is all. Everything you are going to do the rest of your life in IT is based on this thing we are doing here. Take all the courses. Your programming, if you know how this works, programming will be very simple for you. If you know how this works, AI will be very easy for you. If you know how this works, every course, trust me, every course. So IT gets easy by day as you move along. It's very, very easy, very simple, very straightforward. Don't let anybody think that IT is difficult. No, it is not. It is not.
Thank you, sir.
Welcome. 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 Abana is getting worried that when will IT get easy? Abana, IT is easy. Okay, let's solve one more example.
So can I?
Let's solve one more example, then we can go on. So let's see the one example. Who wants to demonstrate one of them? From the labs. Yeah, the labs. Sandra Bruni, your hand is up again. Is it Bonnie? The labs. Let me see somebody else. So one more example. Sandra, can you share your screen once you want to show us something?
Yeah.
Or are they also?
Can you see it?
Yeah, we can see. We can see, so go ahead.
Okay, so please, this is how I understand the LMC. First, you write your program using the assembly language. So the assembly language, the input, we have input, we have store, we have output, add, and the out. So each instruction will be translated into numbers and placed into the mailboxes when you assemble it into RAM. So when you assemble it into RAM, it will translate into numbers and it will be stored in the mailbox. So the PC will be 0. The PC, the program counter will be set to 0. This means the computer will start executing the program from this mailbox here, 0. So the value here will be fetched and it will be given to the instruction register. So after fetching the value here to the instruction register, the PC now turns to 1. The control unit then looks at the instruction in the instruction register and decodes it to understand what operation to perform. So if the instruction is an output instructions, the computer waits for the user to enter a number. So it will give you this one here. If the instruction is an input instruction, the computer will wait for you to enter your number, and the number is placed into the accumulator. The number will be placed here. The input knows what to do because the instruction already stored. The instruction is already stored here. So the computer tells the input. The computer. So because the
Sandra.
Yes.
They're waiting for you. Why you gone mute too?
See, I understand it, no, but how to explain it this is the problem.
Explain it the way you are. Who told you are not doing well?
I think maybe the way I'm explaining it, they won't understand. I understand, but I don't know how to explain it to them.
But who told you are not doing well? Who said it?
We understand, so keep on explaining.
Please,
you
go on. Understand.
You are doing well, so go on.
I understand you, my brother. My brother, I understand you.
I'm not a brother, please.
I don't know your brother, please. Sandra, go ahead.
So should I start?
You are doing just good. So, they are not giving you feedback, and that they understand.
No, say like okay. I think the way I'm explaining the thing, they understand. Okay, so say please, you write your program here.
I like the way you started. Yes, this is an assembly language. These are the instructions. When you run this, it's good. So keep going. They are following. They are giving a lot of laughs and claps.
Okay, so please we write our program here. So at the assembly language code. And when you assemble it into RAM, each instruction turns into numbers. It will be placed here at the mailboxes. And the mailbox, it starts with 0. So immediately we run it and we assemble it into RAM. When the run button is pressed, the program counter, the PC, is set to 0. Because the computer will start executing the program from here. The RAM 0.
Yes, go ahead.
My sister, you are right. Go ahead.
Yeah, please, I'll come and try again.
No. going.
Sandra, you're doing well, eh?
Sandra, I'm fans. I'm fans back.
Why?
I'm fans. Mo be among the fans. Among the fans don't mean Kasebi. Yeah, Rita.
Hello, sir.
Yes.
Please, can you share the screen? I also want to add a bit to what has been explained earlier.
Yeah, you can share your screen and go ahead.
Sir, please, I don't have the screen.
You don't have a screen. Okay. One of you should share your screen for Sandra. Bring back your screen. Mm-hmm.
Can you please add the assembly course?
Yeah. Yeah, how are you? I'm okay. When? Oh, okay. I'll start somewhere. Are you done? Uh-huh. Mm-hmm. Hey, but the person is evicting from your place. Okay. Let me call you back. I'm in the class, so I'll call you in a few minutes. Yeah, Rita, let's go. I think she has some instructions there. Let's go. After this, I think we'll be fine. Then I can move on to today's active session. Rita, can you hear us? If you are speaking, we are not hearing you.
Sir, I wanted to explain the reason why the assembly codes were lined up in the memory boxes like that, but it seems I'm not getting it. that way, so it will be hard for me to explain it.
Charlie. Okay, that is fine. Let me teach a bit. Then
okay, yes, it's okay. Okay,
so you should have told her that click on this to let this happen. You should know that when you have your codes here, if you don't run or submit it, it's not coming here. So once you submit, it comes into the window for execution. Then you can run. Then begins all the internal processes. So now your input output processing is what you say the IPOS cycle. Is when you look at the after the assembly language window. Okay, the next window is just showing you your input output processing store. So this is the entire IPOS cycle, which all of you know the IPOS cycle very well. Okay, so what if you do, you see the difficulty I'm having with you people is that you do not understand even what you have done in computer science 1. And that's why you are struggling in this class. We have not done anything yet too. We are only at the very surface level of things. But you are not reading. You are not putting things from where your previous classes. And it shouldn't be the case. It shouldn't be the case at all. So go back. We are not here to get any kind of half knowledge here. No, you must fully understand everything we are doing here. So anyway, go ahead, Rita. I don't want to.
Okay, so the RAM always has 3 memory addresses. The first one is the opcode, and then the other 2 are the address, the instruction address. So when we take a look at the assembly language code, we could realize that the 00 here is for input, 01 store 99, and then 02 input, 03 add 99, and then 04 output. So the reason why they are lined up here 901399, not exactly as the assembly language code, is that 9 here stands for input output. So whenever you have the code, whenever the instruction is about inputting or output, you are going to have 9. And then when it's input, you have the 01. So when we take the 4 here, it's output. That's why we are having 902 here. And then 1 stands for add. Where is it? So number 3 here is add 99. But then that's why under 1 we are having 399. So 1 here is the opcode, which means add. And then 2, I'm coming up.
Yeah, I mean, if you ask you.
That's why you can write
7.
That's why you can.
We don't understand anything. So we
That's
don't
why you can
understand
read
it.
and write. Be there. With all the explanations
No,
you have, you don't understand anything. What else
let me begin it well. So we have 0, 1, 2. That we have 0, 1, 2. The numbers at the top, they are opcodes, and they each have a meaning. So 1 means add. So but 3, when you take the 03 here, the assembly language here, it means add 99. That's why under 1 you have 399. And then 2 means
so we are teaching.
2
we are
means subtract.
Junior, come on, and then you think you understand. Go ahead. You don't pay attention.
2 means subtract, but we don't have anything subtracting here. And then 3 means store. So
Can you go on? I have to teach, so hurry up so I can, do some 30 minutes teaching.
Someone is muting me, that's why.
Can you imagine?
So I just wanted to talk about the opcodes and then why the instructions are being lined up like that. So one as the opcode means add. So whenever you have the assembly language and you are instructing it to add, it will come to 1. So I just want to elaborate on that.
Thank you.
Please, I'm done.
Yeah, thank you. So on share your screen. Let me share my screen and teach. Thank you very much, all of you who have participated. That is how the class must always be, very engaged. Everybody must share how your work is going on with you. Okay, it's not about me. It's not about what I'm going to teach you. No, it's about how you are going to coordinate the activities and the things we are learning in class. If you don't try it, you'll come and be in the class and say, me teach you as you. And just be there and just say you don't understand. We are moving, so I expect that every one of you will be able to get the whole thing. And another thing is that some of you maybe have not used the binary assembly language codes as well. So what you need to do, maybe to see how the assembly language itself works so that you can understand that framework. So just think about, try and get resources on assembly language. You know how the various mnemonics works. So when you see LD, when you see ADD, when you see SUB, all these are program instructions, and then you must understand them. So I think that is one of the fundamental things I also see as a missing link to most of you in the class, that you do not understand that. So I'll share a book on assembly language programming, okay, with you, so at least you can understand the mnemonics. The mnemonics is the major thing. So if you look at it, just look at how the mnemonics work. So when we say add, the various short ways of representing assembly language are in that book. When you get it, you may not want to study details in whatever is there, but your major focus here is how you look at how the mnemonics works, and then you can understand them when you're writing your assembly language program. It's very important. Okay, so let's make some progress on today's lecture, and then you can follow through what I'm doing. All right, can you see my screen?
Yes, sir.
Okay,
Yes, sir.
so I'm going to explain that iPod cycle again for you, and then you can know the function between these components again, because like I said, it's very important to understand how they work. So we have already understood from our previous lessons the role that John von Neumann played and how today's computer architecture follows the von Neumann architecture. Okay, so data and instructions are stored in a single read-write memory, and that is why, you see, because of some of these ways, some of these have been put together. That's why you must have mental understanding of framework of the little man computer and then the CPU OS simulator, because if you do not understand, have that mental view, you when we tell some of these things, you get lost. So try to understand, have that mental view of things, and then you can be following through better. So memory are addressable by location, and you know it. Memory have addresses. When we say memory are addressable by location, memory have addresses, and that is why we need to know the memory address, and then be able to know what is in there. So we don't really need to know, without regard of the type of data contained in there. All we care about is the address. And if you have done your programming very well, you know that it's just like creating an array. When you create an array, you may not necessarily want to know what is in the content of the array, because you can access the array content based on the array index. Am I saying something that you know already?
No, sir.
Yes, sir.
No, sir.
Yeah?
Sir,
So
please, no.
which one is a no? And which one is a yes? You don't know what arrays are. Is that what you are saying? You don't know what an array is. So if you look at what I have at this part of the screen here, okay, we can call this an array. So look at it, it's the same as the memory, okay? So if I have a place in memory slotted this way, and then we put these numbers. So 1, 0, 0, 1, 2, 3, 4, 5, and 6. Okay, these are see this as the addressable. Okay, and then what is the content here? Let's say 30 in here. I have maybe K here. Okay, I have maybe 40 here. I have maybe Abena here. Okay, I have Abena here. I have maybe Hazel somewhere here. I have 50 here. Then I have Enoch somewhere here. Okay, I have Enoch also here. So the content in this array, the content in each of these, whether the different data type, because you know what data types are. Okay, data types, you can have different types. So here I have number here, I have text here. There are different data types. But what about data types that are stored in there? My main focus is in this memory or this location is that memory are addressable. So I have the address locations here, okay, which is the indexes in the case of array. So this is a typical array, okay, which also works the same way, like you have memory and address. So these are addresses. So to know what is at this location, I cannot know it until I call this. So I have to call maybe array RRY, maybe at location. So I bring this my score and say location 1. When I put location 1 in this box, it will now tell me that what is in location 1 is 30. Okay, sorry, it's K. What's in location 1 is K. So at the end of the day, I am able to know what is in the various locations based on these addresses here, the addresses here. Are you following?
Yes, sir. Yes, sir.
Sir, please,
Yes,
I
sir.
can't see your
Yes, sir.
cursor moving.
You can't see my cursor moving, but can you see some drawings on the screen?
Yes, please, I can see that one.
And then just take the drawings, because the cursor, I wouldn't know why you can't see it. So I'm trying to show that where I have this drawing, okay, the array with the arrows, the down one, the 0, 1, 2, 3, 4, 5, 6 are the addressables, or they are the indexes that can help me be able to tell what is stored in these locations. Okay, so that's simply what is happening. So, and that is how memories actually have been designed. So if you look at a little man computer, it's the same thing. Okay, if I should show the little man computer, it's the same thing that I expect to see here. You see this one? Yeah. So memory in itself, so as you see here, memory are addressable. So it's not the content, which can be different data types that we are thinking of, but the addresses, because based on the addresses, can you see my screen still? Yes, sir. We can see your screen.
Yes,
With
sir.
the little man or the PowerPoint?
The little
With
man.
the little man.
Okay, good. So it's the same thing we are trying to put across that. My focus is not the content that are in these addresses, okay? But once I know the addresses, I can tell whatever is in there. All I need to know is the addressable thing. So that's why it's a memory addressable by location, but without regard to the type of data that is contained in there. So execution occurs in a sequential fashion, okay, from one instruction to the next. That's why all the instructions that we put here, okay, all the instructions we put here, all of them execute sequentially by how they have been written. And then we can have other things processed in there. So these are the various approaches whenever you see a computer. So in the programming, if you are programming in hardware, you need to have your data and then the sequence of arithmetic and logic functions, then you get your results. When you are doing software programming, you need to have your codes or your instructional codes. There's always a compiler or an interpreter who will send some control signals. And then we have the general purpose arithmetic logic unit of the CPU who picks this data and then transfer and gives them the distance. So between you and the CPU, when you are writing computer codes or doing programming, is the interpreter or the compiler. I hope you know what the compiler is or the interpreter. You know what the compiler or interpreter is?
Yes, sir.
So that is you are sitting somewhere here. You are here. You are right. You have your PC before you. You are writing your codes. Okay, you have your computer codes here. So once you write your instructions or codes, it does not come here directly. Okay, it doesn't come here directly. No, it's an error. What does it go to? You need a compiler or an interpreter because your instructions you have put here are what? High level, right? They are HL, high level language. So that we need a compiler interpreter to work on them. Then you can have them also giving some signals to the systems. I mean, the CPU picks up whatever it is, and then there we go. Are these concepts clear?
Yes, sir.
And that is what is happening here. It's the same thing.
Yes,
the
sir.
CPU is doing the job. It picks all those instructions. So this is assembly language. That's why. So this is your editor. So the white area is your editor, your writing pad. When you write your writing pad and you push it, it comes into the interpretation area. And then we now can run it for the system to pick them up. And then we move. These are the same things you are doing here. You have written programming, maybe, I don't know the language you've done so far, maybe C++, maybe Java, maybe Python. You've done all these languages before, right?
Yes, sir.
So some of them, yes. Don't you write on test editors?
We do, sir.
Don't you push the thing to compilers?
Yes, sir.
Yes, sir.
So what is your problem that we don't understand what is assembly language code? We don't know what goes on. My friends, you better open your eye and shine your eye. And then connect the things you are learning together. Because learning should be transferable. You don't learn one side and forget and come here and expect the other teacher to repeat all what the other teacher has taught you before. Otherwise, how can we get knowledge and move on? So that's very, very important concept that you have to understand. So your software and I/O components, software, you have all your sequence of codes or instruction. They are part of the hardware. They interpret each of the instructions and then you move through. But the major components of what these things happening is what? Your CPU and then your I/O components and then your output model. And that's what you see right there in Letterman. Your CPU, your input model, your I/O output model. It's exactly what you see. Okay. And once you have all these major components, you know what each of them is doing. Because it's not today that you know that the CPU has instructions and they have arithmetic and logic unit and they do all this. These are common knowledge to you. So we don't spend time here. Now the MA and then the MBR, the memory buffer register, the memory address register, the IO address register, and then the IO buffer register. So these are very critical registers that are required within the system. Very, very, very important components. So an input device, for example, okay, will bring the instructions and then the data will also be brought sequentially. But anytime the program is not executed the way they have to be, then it means that other instructions are in between them. For example, there can be jump instructions. So then we expect that instructions will go sequentially. But what about some of the jump instructions can be, for example, I have a program that is running this way. Now along the line, I can put a jump instruction here. So jump. So where is it jumping to? It's jumping perhaps to jump to A. Maybe A has been defined here, okay? So now A will come and whatever is in A will be executing. Then perhaps it will get to a point that it has to come back to this area again and continue the execution. So we have those instructions that do not allow all the time programs to be executed sequentially because of the jump instructions. Or we also can sometimes have some of these sequences predefined in a way that if I should use if else, for example, which may be familiar to you in modern times. So say if whatever instruction, do something. So do certain things. Else, right? Else come and do certain things. So when the program is running and this condition here is not met, if this condition is not met, what do you expect? The guy will jump and come to this guy, right?
Right,
Yes,
sir, right.
So the memory address register will specify the address in memory for the next read or the next write. So note that carefully. When you see the memory address register, then the buffer register will also contains the data to be written into the memory or to be received from the memory. That's what the buffer. Buffer actually is storage. So if you know your terms well, buffer normally relates to storage. So once you see address, it tells you are looking for the next read or next write. Address, buffer, you are looking at what should be held. Okay, so written into or received from memory. So then if I have the IO address, which is going to work with the memory address register, then we will look at the type of IO device that is going to work to do that, because the address. Then the IO buffer will also be used, the type of IO device that will be used for that exchange between the actual model memory and then the CPU. Simple knowledge. And that's exactly what we are doing here in the here. So the instruction registers are all there. In fact, the reason why we are using the the CPU simulator was to let you now see all the other registers. So by that, if you recall, you saw all the various registers, the memory address register, the memory buffer register, the instruction register, all of them within the CPU simulator. For you to understand the registry, let me go on here. Okay, the registry component. So within the CPU, we have the program counter, the memory address register, we have the instruction register, we have the execution unit, we have the IO address register, the IO, what I just showed you. So with this CPU, it is connected to the memory, which we see right here. You can see a CPU is connected to a memory, and then the CPU is connected to what? The IO module. Can you see right there? CPU connects to IO module, which is here. Are you following?
Yes, sir.
Yes, sir.
Yes, sir.
So this is the exact computer you are working with. And you must understand the workings, these internal workings, because that is how the system works. So CPU always connects, has a system bus that connects to memory, and a system bus that connects the IO. So this IO model in the little man, this is the O, and this is the I. So IO. And each of the models contains what is holding CPU, and then CPU is connected to the memory. So if you have this thing in mind, trust me, you'll be a better computer scientist. You understand whatever is happening. You know how to do and how to do it at what point in time. You know your memory is constrained, so the kind of algorithms are going to write. You know how to optimize them to get the best. That is why you must understand how the computer works. Architecture and organization. And that is very, 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 very important. Very important. Now from here, what do? We try to understand that when the CPU is working, all the basic instruction cycles. So take note of it. It is the start, fetch the next instruction, execute the next instruction, halt it. So if you see, we write our instructions. I can write in here. At least you remember the codes you're writing. We start, we write, we write all the instructions. When we are done, we halt, and then we move. So that's why the halt is there. So we start and halt. Okay, but the rest of the instructions will be fetched in there. So we have the fetch, decode, execute cycle, or the first cycle, the execution cycle, which is very crucial. So what does the first cycle do? The first cycle will look at all the various instructions, the processes, or things we need to fetch. The program counter is here to hold the address of the next instruction. Then the processor will have to increase the program counter after each of the instructions has been fetched. The first instruction will be loaded into the register, and then it will be moving on. Do you see it? And that's why I needed you to practice this. So I thought we are talking about this lesson. You mentally are ready, you understand everything because you have demonstrated it. If I teach you this lesson right now, and you do not understand how this work, well, I'll just be talking about stars. But I know by now you appreciate why these things are happening the way they are happening, because at least you have opened a human being, you have seen where the intestines are, and therefore you know what to do. You know what to do. So your processor memory, which is more tailored toward data transformation or transfer between the memory to memory, or from memory to processor. Okay, then the processor I/O, more towards the peripheral device, transferring between them to the processor and the I/O model. Then the instruction, the controls, which also are specified here, and the others there. So trust me, you are there, right? Any question?
All right.
Any question? Tell me. Are you following the lessons now? Are you appreciating the knowledge?
Yes, sir.
Yes, sir.
We following it clearly, sir.
Yes, sir.
Yeah. Life itself is short. If you fail to make progress, you are in trouble. Okay. We are ending here. Recap. Abena, where are you? Your plate is full. Recap my lesson today. What have you done today? And let me go. I'm going to sleep. You said you are sleeping. I'm going to sleep. Recap. All we've done. Now the full lesson. Whatever I'm teaching you here have been demonstrated already. So it's just for me to highlight all of them to you for you to see why things are what they are. So recap for me and let's see. So the various opcodes or codes we're talking about and the address part. So every instruction format has the opcode part and then the instruction part, the address part. Okay, and then we're able to compute them. So the program counter will always be equal to the address of the instruction. The instruction register will always be equal to the instruction being executed. The accumulator is the temporal storage. And you have your internal CPU registers, which are these guys here. So when we load from accumulator from memory, we can also store accumulator to memory and add to accumulator to memory. And that is how we can store these opcodes. So then if you look at the various systems, how the memory and the CPU are working, this is how they really, when you see program execution in the system, every time we go to, so that's the memory addresses, right? And we have said that whatever memory is holding self-contained is fine, but we can always go and fetch the instruction, okay? Then when we go and fetch the instruction, immediately program counter will be holding the address of the next instruction, because that's what it's doing. Okay, so the next instruction is 301. Program counter is already holding the next address of the next instruction. So memory has addresses which are addressable, and the system goes to pick them. The accumulator is now adding up. So accumulator was nil here. Now we have something called accumulator is adding up. Accumulator keeps adding until we are able to get all the instructions fetched and everything is done. Are we good?
Yes, sir.
Sir, please,
Sir,
can you take this
Take it
particular one?
again.
Yes, sir.
Oh, time is up. It's 5:30. Take what again? Everything I've said is
Sir,
the same.
this particular one.
Sir, please exercise patience to us, okay?
Figure 3.5.
Who told you I'm not as patient? Do you know how I'm teaching you very patiently?
Sir, please, we beg.
You beg for what? Somebody should tell me what I just explained. One of you should go by it based on the understanding. Who wants to try?
That's why we say you should go over.
I'm not going over. One of you should tell me what you understood. You can't tell me all the 124 if you one person didn't understand it. Anyone want to try? Try and I'll fill in. Who?
Please, can I try?
Yeah, try.
Wilson.
So, from what I heard,
yep.
In the first box, the instruction register goes to the first address in the memory side, which is the 300. It picks the instruction there. Then the program counter goes, it now holds the address of that particular memory. Accumulator has nothing because there's nothing in there. That's the step one. Then we go to step two. Step two holds the program counter holds the address of the next instruction. The next instruction is to be run, which is the 301, and then accumulator holds 003. Sorry, that is why I don't know that's what I don't know where it's coming from. So if you can,
what is the accumulator doing? How did I explain the accumulator?
Okay, so accumulator is performing a logic or arithmetic, something like that. So now the instruction is in the accumulator.
Take your time. What did I say the accumulator holds at every given time? So this place, don't forget remember this particular 301 is the next instruction to be picked up. It's here. But
yes,
what you'll see here is the instruction we are processing. But yes, the CPU knows that after finishing this work, he's going to pick the next instruction, right? Which is right there, which is the content of this guy here. But it's 301 we are interested in, not the content per se. Because once we know the address, we can know what is in there. It's just like your mailbox in a post office. Nobody wants to know what is in there. But once we know your address, you can open your address and we can get the content of your box. So this is exactly what is demonstrating. You know your post office number is VV40. Okay, so when you go to a post office, this VV40 box here contains a series of things here. They are there. But you don't know what is in there. And that's not your case. All your case at all times is to know your address. Because if you don't know your address, you cannot open your mailbox. Right? So we need to know the address. So CPU is always tracking the next instruction. So at this point, you see accumulator will be holding the next instruction. At this point, you see accumulator will be holding the next instruction, which is next till we get to the last step. So the idea is that if you take the memory and the CPU registers, the instruction register is interested to go pick what? The various instructions that needs to be worked on. Okay, so it goes to fetch the instruction and load the instruction into the instruction register. So once it loads the instruction register, then we can get the PC quickly updating its memory that this has been fetched. So the next instruction to be fetched is this one. The CPU is well aware that it's going to put the next instruction. Then accumulator is counting. It's counting. It is accumulating. Now, so I say it's a temporal storage. If you have listened, it's a temporal storage. So it's going to store all the things that are happening, and counting them in that order. And that is what the accumulator is doing. Accumulates. So accumulator, it accumulates. And that is its function. So these are very important things. So when you see the 300, it is just the address of the first instruction. But the value of the 300 is what? 1940. That's the value in there. And that value is loaded into what? The instruction register. And then the program counter is incremented. So it is just a counter. So program counter. It is incremented. So once it is incremented, that's what you see right here. Okay. And that is the that incrementation is done using what? The address register and also the memory buffer register. And that is what normally it happens in there. So the next 4 bits which are going to be picked up from here will be on 301, which will be the next instruction to be fetched. So when the system goes to 301, then the program counter will be incremented. Then it will now go and pick the various things again until it's able to store all the elements in there. And that is how these things are working. So the same internal processes that are here. The program counter is counting. The instruction register is going to pick the instruction for us to know where we are. The accumulator, it's telling the next instruction to pick. Then the accumulator is counting whatever we have in there. So these are very important registers that are in the CPU that makes the work of the CPU more easy and more efficient. All right, so read more and then you should understand whatever we have done. I'll share some more activities to you on Sakai. And then, like I said, watch the course outline carefully. There are quizzes that are due, and then there are activities that are due. Make sure you watch the space and get it done. Thank you for coming. But you need to practice more. If you fail to practice on the 2 simulators I've given you, there's no amount of explanations I'll give you in class because the simulators are very critical. Yes, Richard.
Sir, please, I just wanted to remind you, said you send us a book containing the codes.
Which codes?
You said you send us a book which contains the explanation of maybe the
assembly language code.
Assembly language.
Yes.
Assembly language.
Yeah.
Okay, I'll look for one and send. But you can also check online and look for any assembly language book. It's just the mnemonics you need to know. So when we say load, when we say add, when we say subtract, when we say multiply, it's just because now all you know is your normal high-level programming language, right? Which is either your C++ or your Java or your Python. This is an assembly language. It's also a programming paradigm, right? Like the machine language and now the high-level language. So we write them using the assembly language codes, which you can get in a book online, then you get it in there. But I also look for one and share with you. But if I have not sent, don't wait for me. You can always look for a book. The internet is huge. You can look for a book and then get things done. Yes, yes. Enoch.
Yeah, Zed. So I wanted to find out how you were able to install the CPU OS simulator on your.
On what?
On the MacBook.
You follow the same instruction on the page. On the link I share with you.
Okay, sir.
Yeah, so that's it. It is not anything strange or anything new. It's the same thing. So practice, okay? You need to just practice. If you go to the page I shared with you the last time, the instructions are there for you to set it up. It's not anything different from all the other ones that your colleagues have done. I'm not using Mac. So the Mac instruction was there. So just follow the Mac instruction on the page. You should be fine.
Okay, sir.
Any other question? I can check CPU OS, CPU OS simulator. This one or this one. Yeah, I think this one. Yeah, I think that is the one that you have to check when you unzip it. When you unzip it, I think you need to rename it to what was given to you on the side. So once you do that, you should be able to get it working. If that one is a bit, you can check other ones. If that one is not working on your iOS, okay, you can look for there are other versions of the CPU sim that may be able to work on your your iOS device. I'll check. If I find another one, I'll share with the class. But the one I have is what I shared the other day. CPU sim iOS for Mac. Let's see no, I think I'll have to check. I'm not too sure the one here. So when I find any new one that suits Mac, but the one
No, please, you are muted.
Yeah, I was saying that those of you who have the links to the simulators, share it to your class group and let them have access to it. So we'll meet you next week. I'll share activities on the field, so be following, please, so I don't miss them.
Okay, sir.
Good.